All right, welcome back to your first digital lecture. As some of you might have heard me mention before break, this is going to be a double lecture, so you will have week 9, day 2, and week 10, day 1 to watch today and corresponding daily homeworks for both. So just to give you a rundown of any assignments we have ongoing that you might have forgotten about, there is, for daily homework due today, none. I am giving everyone full credit on any daily homework that would have been due today or last Friday. But you will have daily homeworks, 2 of them, due on Friday. One of those will be for week 9, day 2, this lecture, and it will be section 8.10, problem 4, section 8.11, numbers 13 and 15, and section 8.12, number 2. There will also be a daily homework from week 10, day 1, that is chapter 12, section 1, numbers 2 and 3, and then chapter 12, section 2, number 1. Don't forget that test 2 is due Friday as well, and you'll submit that by Moodle. And periodic homework number 5 is due next Tuesday, a week from the date of our normal lecture, if you're watching this on the normal schedule. I know this seems like a lot, and to be completely honest, it is a lot, but we need to get back on schedule after missing a lot of late last week due to the last-second graduation type stuff. So, a little bit more work to get back up to speed, but then things should settle back down. So, the first thing we're going to talk about today is something called a convolution. And convolutions are a way to take the inverse Laplace transformation in a certain situation. And to get an idea what this situation might be, let's consider the following differential equation. A linear second-order differential equation with constant coefficients, like we've been working with, but a times y double prime plus b times y prime plus c times y equals some function in terms of t. And if we were going to try to solve this by Laplace transformations, well, we would take the Laplace transform of this whole equation. Let's, for the sake of brevity, let y naught and y prime naught both equal 0. So this Laplace transform is nice and easy. So for the first term, we get a times p squared times big Y, where big Y is the Laplace transform of little y. For the second term, we get b times p times big Y, then c times big Y equals some function capital F of p, where this function capital F of p is the Laplace transform of f of t. So if we want to solve for y, we would end up with y is 1 over ap squared plus bp plus c times big F of p. And then we would be left with the task of determining the inverse Laplace transform of this function right here. Well, we might know how to take the inverse Laplace transform of this half. That denominator could be factored. It's a quadratic after all, and there's probably something on our inverse Laplace transform table that would let us do that. And then maybe we could find the inverse Laplace transform of f of p separately, but these two functions aren't added together, so the rules we've learned already won't work. So we want to know how to find the inverse Laplace transformation of a product of functions. where we know how to take the inverse Laplace transform of each one of these two individually. We just don't know how to take the inverse Laplace transform of the product. And that's what a convolution will do for us and why we care. So let's just set this problem up first. Let's let our function big Y be equal to big G times big H, and define some things. Where big Y is the Laplace transformation of our function little y that we're trying to find, big G of P is the Laplace transform of the function little g of t, and big H of P is the Laplace transform of the function little h of t. And our ultimate goal here, which I'll draw in orange up here, is to write this product in the following form. As some integral from 0 to infinity of e to the minus pt times something. dt. Because this then would just be the formula for the Laplace transform of whatever that something is. So the something here would be the inverse Laplace transform of big Y, exactly what we're trying to find. So our whole goal here is to rewrite this function for Y in this form we've laid out here in orange, and we're going to do that in a few steps. First, I'm just going to take the starting definition of Y and write that out in integral form using the Laplace transforms. So G of P, the Laplace transform of little g, is just the integral from 0 to infinity of e to the minus pt times g of t dt. And big H is just the integral from 0 to infinity of e to the minus pt times little h of t dt. Now we're going to do something that seems like a little bit of mathematical trickery, but it's going to help us work towards the end we're looking for. In our first integral, we're going to rename a variable. Instead of t, we're going to use sigma. And in our second integral, instead of t, we are going to use tau. So not changing anything specific that we're doing, the same integrals involved, just giving some variables some different names. So then our integral becomes the integral from 0 to infinity of e to the negative p times sigma times little g of sigma d sigma times the integral from 0 to infinity of negative p tau h of tau d tau. And now, since we have two integrals in terms of different variables, one is over sigma, one is over tau, we're going to combine our integrals into one. And write them all as one integral. We can do this because tau and sigma are independent of each other. So we have the integral of 0 to infinity of the integral from 0 to infinity of e to the minus p, combining our exponential terms, sigma plus tau times g of sigma times h of tau d sigma d tau. Well, we're starting to get a little closer to what we're looking for at the end here. We have an e to the minus p times something term, and we need an e to the minus p times something term at the end of the day. So we're going to do another change of variables here. And that change of variables is going to be that we're going to let t equal sigma plus tau. And that would leave us with an e to the minus pt term. So if t becomes sigma minus tau, that means this part will become t. Sigma, this part here, well, sigma is going to be t minus tau. And d sigma. To figure out what d sigma is, will turn out that d sigma is just equal to dt. Because the integral for sigma is within the integral for tau. So while we're doing the integral over sigma, tau is constant. So we're just left with d sigma equals d tau. And then the last thing we need to change is our y. Why did you do that? Okay. This lower bit of this integral here is when sigma equals 0. And sigma equals 0 when t equals tau. So I'm now going to rewrite this whole integral here. So we still have the integral from 0 to infinity for the outer integral, the tau integral. But for the inner integral, we now have the integral from, and let's actually be really explicit here. Since this is the tau integral, this is the integral from tau equals 0 to tau equals infinity. And then the second integral goes from t equals tau up to t equals infinity of e to the minus pt times g of t minus tau times h of tau d tau dt. So we are almost to the goal that we have here up in orange at the top. We have an e to the minus pt. We have something, but... oh, my integrals jumped ahead here. The way we have this now, it is the dt integral on the inside and the d tau integral on the outside, which is exactly the problem. We want this outer integral to be in terms of t, not tau. So we need to switch the order of our t and tau integrals. And to see how we might do that, let's consider the tau t plane to get an idea which combinations of t's and taus we're accounting for with this integral and how we could rewrite it in the opposite order. So we integrate in terms of t from t equals tau, there's the t equals tau line, to infinity. So, well, here's t equals tau, and there's t equals infinity out there. So we'd be integrating in terms of little chunks like this, from t equals tau up to infinity, and then let tau go from 0 to infinity. So we'd be accounting for all of these strips this way. So this is, first, tau is integrated from, t is integrated from tau to infinity, and then tau is integrated from 0 to infinity. To reverse the order of this, we instead want to find a chunk like this, and then add up these vertical strips instead to account for the same total area at the end of the day. So with this setup, first, we integrate tau from 0 to t, and then we integrate t from 0 to infinity. So in our quest to reorder these integrals, we can instead say that y, big Y, is equal to the integral from, again, let's be very clear here. Where are we? There. From t equals 0 to infinity on our outer integral, and from tau equals 0 to tau equals t on our inner integral, e to the minus pt times g of t minus tau times h of tau d tau dt. Does this look familiar just yet? Well, I'll write it one other way to show us what's going on here. We now have y equals the integral from 0 to infinity of e to the minus pt times the integral from 0 to t of g of t minus tau, h of tau, d tau, that whole thing dt. Now does this look familiar? This something that we were trying to find before is this term right here. So we have arrived at our final answer here. That our function y, that was equal to big G of p times big H of p, is the Laplace transform of this integral from 0 to t of g of t minus tau times h of tau d tau. So this right here, this function, is called a convolution. Let me outline it in, we'll say, pink. Is the convolution of little h and little g, which is written as g star h. And if you want to know what types of algebraic operations are allowed with convolutions, I recommend you dig through the sections in the book to find some of those, because there's definitely some helpful things in there you should know, but I don't want to take up too much of your time with this video. So that's what you need to know about convolutions. Why we would take it when we have a situation where the Laplace transform of our answer is the product of two functions. And we know the inverse Laplace transform for each of those two functions that are being multiplied together, then we would use the convolution to find the inverse Laplace transform of that product specifically. So that is everything for convolutions. The next thing we're going to talk about is the Dirac Delta function. And the Dirac Delta function is useful when you have impulse forces, or forces that act effectively instantaneously. I'm going to put instantaneously in quotes here, because it could be approximately instantaneously. So, relevant physics formula here might be Newton's second law, that force is the rate of change of the momentum, which can be rewritten to say that the change in momentum of any given object is the integral of the force applied over some time. Well, there's a couple things that need to be true if we want this force to act instantaneously. If we want an instantaneous force, or an instantaneous impulse, that means F can only be non-zero at a single point. But for the object to move, for its momentum to change, we need delta p, the change in momentum, to be non-zero, which means the integral of f dt also can't be equal to 0. So we need a function that is 0 at every single point except 1, but it has a non-zero integral. And this is our Dirac delta function. Defined as delta of t is infinity when t equals 0, and 0 for every other value of t. But with the additional property that the integral from negative infinity to infinity of the delta function over time is defined to be 1. So that is what a Dirac delta function is, and we want to think about some helpful uses of this in physics, because there are a ton of uses of the Dirac delta function in physics. But first, we're going to go through some useful relations involving the Dirac delta function. One of the most useful things a Dirac delta function can do is help us pick out a specific value of a function. So if we take the integral from a to b of phi of t times the Dirac delta function of t minus t naught dt, well, we want to think about what the answer to this could be. The Dirac delta function only has a non-zero value when the inside of it, when its argument equals 0. So that happens at t equals tau. So if t naught is between a and b, we're going to get a different answer to this than if the t naught is not between a and b. If t naught is not between a and b, then our delta function has a value of 0 for the entire integral, and we'll get a value of 0. If t naught is between a and b, we'll get a value of infinity for the Dirac delta function, but only at t equals t naught. So this integral is only non-zero when t equals t naught, and the Dirac delta function integrates to 1. So what we actually end up with here is just phi of t naught. The Dirac delta function has picked out a specific value of t. When we multiply our Dirac delta function by some other function and integrate, then we pick out some specific value. This can also be useful for derivatives of the Dirac delta function. For example, the integral from negative infinity to infinity of, again, phi of t times the nth derivative of the delta function t minus t naught dt gives you a value of negative 1 to the n times the nth derivative of phi evaluated at t naught. So by using derivatives of the delta function, then you can pick out specific values for the derivatives of this other function we multiplied by the delta function. There's also something called the step function. I know it is the Heaviside step function. Which is useful for defining when something happens and when it doesn't. So things that start happening at a specific point. The Heaviside step function has a value of 1 when its argument is greater than 0, and a value of 0 when its argument is negative. So the Heaviside step function here looks an awful lot like this. It's 0, 0, 0 up until t naught, and then it jumps to 1. And I guess I could draw you what the Dirac Delta function might look like as well. Zero, 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 infinity, then back to 0. So the Heaviside step function, if you multiply it by something that depends on time, it just specifies that it doesn't exist before t equals 0 and does exist after t equals 0. And these two functions are actually related to each other. That the derivative with respect to time of u of t minus t naught is the delta function. So we go from, if we take the derivative of this function here, we have 0, 0, 0, 0, 0 slope, infinite slope, then back down to 0 slope. But enough of a slope for that instantaneous amount of time for our value to have changed by 1. There are some other useful qualities that delta functions can have. Just some that I'm just going to type out or write out for you. X times the delta function of x equals 0, or correspondingly, no, we'll get to the rest of them. But x times the derivative of the delta function is just the negative delta function. X squared times two derivatives of the delta function is just 2 times our delta function. There are also some random identities that might be useful. One is that it doesn't make a difference if you multiply the interior of your delta function by -1. You don't change the value. But for derivatives of the delta function, at least for odd-numbered derivatives of the delta function, you do. Oops. Pick up a negative. So even-numbered derivatives of the delta function are even functions. Odd-numbered derivatives of the delta function are odd functions. If you have the delta function of some constant scalar times x, that becomes just the delta function of x over the absolute value of a, where a cannot be equal to 0. If you have a delta function of x minus a times x minus b, that is the two delta functions added together, delta x minus a plus delta x minus b, all over the absolute value of a minus b, where a can't equal b. And last but not least, or at least for now, the delta function of a function equals the following expression. The sum over I of delta function of x minus xi divided by the absolute value of f prime of xi, where f of xi are the zeros of the function with a non-zero value for the derivative. Real quickly, I just have a couple more things to write down about the delta functions. We can have delta functions in 2 dimensions and 3 dimensions too, where you might just say delta of vector r minus vector r naught is the same thing as delta of x minus x naught times delta of y minus y naught times delta of z minus z naught. Or, this was in Cartesian, in cylindrical coordinates, we have something similar, but we have extra terms. Just like we do when we find the volume element in cylindrical coordinates, it is not just dr d theta dz. We have that extra term. Usually it is an r dr d theta dz. And that extra term that we get just ends up going down here in the denominator of this expression, so that at the end of the day, we would get the appropriate value here. And last but not least, for spherical, we have delta of r minus r naught, delta of theta minus theta naught, and delta of phi minus phi naught over r squared sine of theta. Math people, come on. Why are you like this? Just stay still. Or math people, this theta is the angle from the z-axis. We are using the physicist definitions here. All right, one last topic for today, and then that will be it, at least for this lecture. Again, sorry for it being such a long one. And this is green functions. And is a useful way to solve ODEs, specifically inhomogeneous differential equations. We're going to be looking at the equation y double prime plus omega squared y equals f of t, with y naught and y prime naught of 0, where this f of t here is known as the forcing function. And we're going to find the solution to this equation, this differential equation, by basically making use of delta functions. So the first thing we're going to do is think about some solution to this equation when f of t is equal to a unit impulse delivered at time t equals t prime. And the solution to this is called a Green's function. So, let me write that out. So the solution to this is the Green function that we will call big G of t and t prime. So it is a function of t, but it also matters when this unit impulse is delivered. So this means that d squared by dt squared of g of t, t prime, plus omega squared times g of t and t prime equals the delta function, t minus t prime. And this right here is going to be our Green function. Then we think about our actual f of t as a sequence of a bunch of unit impulses. Which allows us to write f of t as the following integral. The integral from 0 to infinity of f of t prime times the delta function t minus t prime dt prime, so that at the end of the day, this allows us to find y of t by the following integral. So y of t is the integral from 0 to infinity of our Green's function, g of t, t prime, times f of t prime, integrated over dt prime. And this will be the actual solution for this problem. So we're going to do an example of this. It may not be the most detailed example in the world, but it will give you a very good idea of how we might use Green's functions. The whole idea here is that homogeneous differential equations are easier to solve than inhomogeneous differential equations. And what we really have now when we replace f of t with the delta function is a differential equation that is effectively homogeneous at all points except t equals t prime. So we'll have separate solutions before t prime and after t prime that we will make match up. But that's still an easier problem to solve because it's homogeneous. So let's now do a fairly simple example. Y double prime plus y equals f of x. And let's say this is maybe a boundary value problem where we have a string on a guitar that's being plucked. So we want to specify that y has to equal 0 at x equals 0 and x equals pi over 2, which is a realistic criteria we might have to meet, and it will make our math a little bit easier. So our first step is to let f of x become a delta function, x minus x prime. So that leaves us with the following integral. The double derivative in terms of x of our Green's function plus our Green's function equals the delta function x minus x prime, which, as a reminder, equals 0 for all x that are not equal to x prime. So what we're going to do here is look for separate solutions. Oh, that's a terrible K. There we go. So we're going to look for solutions for x that is less than x prime, but still in this window we're dealing with, and for x is greater than x prime, but again, still in this window we're dealing with from 0 to 2 pi. So, and reminder, this is equal to a delta function. So we're effectively solving the homogeneous version of this differential equation. So we think about which type of functions, when we take the double derivative and add it to the function, do we get 0? And the answer is sines and cosines. So we can write down a general form of our solution for g of x and x prime of, well, when x is less than x prime, we need our function to be 0. If we need y to be 0 at x equals 0, we're going to need g of x, x prime, to be 0 at x equals 0 as well. And that happens when we have sine, because sine of 0 is 0. So we're going to have a sine of x as part of our solution for when x is between 0 and x prime. But there's nothing stopping us from having some other function in terms of x prime act as a coefficient for this. So we really have a as a function of x prime, not x, times sine of x. For the other side of x prime, where x is between x prime and pi over 2, well, y equals 0 at x equals pi over 2, so this Green's function must also be 0 at pi over 2, which happens when we have a cosine of x. But once again, we could have a coefficient there, b of x prime, so some polynomial in terms of x primes. So now we want to try to match this function at that point, x equals x primes, because our function g of x and x prime can have cusps, but no discontinuities. So that means if we plug in x prime to both of these, the edges of the sides of this function at the point where they meet, they should be equal. So we can say that a of x prime times sine of x prime has to be equal to b of x prime times the cosine of x prime. We also know something else. We know that there is a unit impulse being applied here at x equals x prime. So that means the change in the slope of our Green's function evaluated at x prime has to be equal to 1. Since a unit impulse is delivered, the derivative of our function will increase by 1. So similar to how when we had a unit impulse of force, the momentum increased by 1. So, well, let's figure out what d by dx of our Green's function is. And we get a of x prime times cosine of x when x is less than x prime, again, greater than 0, less than pi over 2. And we have negative b of x prime times sine of x when x is greater than x prime. So, taking this criteria we just talked about, because this is a unit impulse, that means the slope after x prime, immediately after, which is this function, minus the slope before, which is a of x prime times cosine of x prime, has to equal 1. So now we take these two equations, this equation and this equation. We find the following: that a of x prime is negative cosine of x prime, and b of x prime is negative sine of x prime. So now we finally know our Green's function. We know what the solution to this differential equation would be if we applied a unit impulse at x equals x prime, and it is the following: negative cosine of x prime sine of x when x is greater than 0 but less than x prime, and negative sine of x prime cosine of x when x is greater than x prime but less than pi over 2. Now, it might not seem like it, but we're actually kind of done here. So now we can just write the following. We can find the solution y of x by the following integral. The integral over all of the space we care about, 0 to pi over 2, of our function g of x and x prime, let me make that a little nicer, times our original function f of x, but in terms of x prime, dx prime. This function here, this f of x prime, is this function here, f of x, just with x primes plugged in instead. So, writing this full integral out, it would be negative cosine of x times the integral from 0 to x of sine of x prime, f of x prime, dx prime, minus sine of x times the integral from, let me double check something here. Something seems a little weird. And I want to make sure it's right before I write it down. No, that is not right. Okay, the integral from x to pi over 2, that makes more sense, of cosine x prime, f of x prime, dx prime. And now all we need to know is which actual function, f of x, are we dealing with in this problem. And that is what at least one of your homework problems is about, is solving this integral that I've just written on the board and boxed for a specific value or a specific function, f of x. So you can skip all of this derivation that we did to get to this point and just plug it into the integral I have boxed. But at the end of the day, Green's functions are a common way to solve differential equations that allow us to solve the homogeneous version of the differential equation first, which is the easier one to do. So don't forget all of the assignments that I mentioned at the beginning of this video. And when they are all due, please feel free to email me if you have any questions or don't think you'll be able to have reliable internet access or anything like that. But if I don't hear from you, I will expect all of your daily homeworks emailed to me in PDF form by the start of class on Friday, and all of your tests turned into Moodle by the start of class on Friday as well. All right, thanks for watching, and have a good day.